What's going on, guys? Hope you're doing awesome. So in this tutorial, we're going to do the coolest project ever. Basically, what we're going to do is we're going to create our own Google Translate. Well, sort of. Specifically, we're going to implement a sequence-to-sequence model using LSTMs on a dataset with German and English sentences. But before that we do that, let's play that beautiful intro. So I went through the sequence-to-sequence paper in my last video, but for those of you who didn't watch that one, let me do a quick 30-second recap and let me bring out this figure right here. So this beautiful figure, what we're gonna have is we're gonna have two LSTMs. So we're gonna have this left one right here, which is called the encoder, and it's gonna take the German sentence and it's gonna produce this red box right here, which we're gonna call the context vector, or Z. And this is gonna be input to the other LSTM, which is gonna be called the decoder. And essentially this one is gonna take a start token and then it's gonna start predicting these words, these translated words, and cell by cell, it's gonna produce the output sentence. All right, that was a bit longer than 30 seconds, but never mind. Let's get started with the code. All right, so let's start with our imports, and I'm gonna cheat, don't be mad. I'm gonna copy those in right here. So we just have, Torch, and we have Torchtext, which I've made tutorials of, if you wanna watch those. And we're gonna import the multi-30K dataset, which is, as I said in the intro, a German to English dataset. And then we're gonna import field and bucket iterator for the pre-processing. We're gonna have NumPy, we're gonna have Spacey for a tokenizer, and then we're gonna have TensorBoard just to get some nice cost plots or loss plots. So anyways, let's first do the Spacey ger to be spacey.load of DE, which is gonna load the German tokenizer. And sorry for those of you who watch my Torchtext tutorials, I'm gonna go through basically the same thing. So Spacey English is spacey.load of English. So this is going to be our English tokenizer, and we're going to define tokenizer in German. It's going to take some input as text. Then we're going to return tokenizer.text for tok in spacey germ.tokenizer of some text. All right, so it's just going to take some text, some text in German, and it's going to output. So basically, if I have hello, my name is, and it's going to output basically a list of hello, my name is, something like this. So it's a tokenizer, and that's what it does. So I'm going to do the same thing for the English one. Also going to take input some text, and let's just copy this in right here. So tok.text for spacey _ English tokenizer. All right, so let's now construct our field, which is we're gonna define how the pre-processing of the text is done. So we're gonna do field, and we're gonna do tokenize equals tokenize German, and then we're gonna do lower equals true to make everything lowercase, and then we're gonna do init token to be start of sentence like this, and end token to be end of sentence like this. And then we're gonna need one for our English text as well. So we're gonna do English equals field. So I'm rushing this a bit because I've made this in my previous tutorial. Watch this if you want. Watch those if you want more info about this. This is kind of just coding it for the sake of coding it, I guess. So then we're gonna do lower equals true, and we're gonna do tokenize English. So now that we have those, we can use the multi-30K dataset. So we're going to use train data, validation data, and test data to be multi-30K dot splits. And then extensions are, we're going to have dot .de for the German one, and then we're going to have dot .en for the English one. And then we got to define our fields, and our fields are going to be German first to match the first in the extension, which is DE for German, and then we're gonna have English. Okay, now that we have our training data, all that we need to do, or I guess there are two things we need to do. First, we need to build our vocabulary. All right, easy enough. We're just going to do German.build vocab on our training data. And we're also going to define sort of a max size of the vocabulary. So I don't know, 10,000, something like that. And we're going to use a minimum frequency of 2. So essentially, if a word is only repeated once in the entire data set, we're not going to add it to a vocabulary. It needs to be at least 2 times. And then we're going to do English.build vocab of training data, and max size is equal to 1,000. Yeah, I should have copy pasted this. So minimum frequency is 2. And yeah, all right, now we come to the fun part. We have one more thing to do with the Torchtext, which is define our bucket iterator, but we're going to do that later on. And that's the only thing we have left. So what we have is actually, implementing the model. So we're going to have class encoder and then module. Let me just do a pass so we can see sort of the overview of what we're going to do. We're going to have an encoder, right? The first LSTM, and then we're going to have decoder, which is also going to inherit NN module. That's the second LSTM. And then we're going to have another, so Seq2Seq. It's also going to import NN module. And so essentially, this Seq2Seq is going to combine the encoder and decoder. Okay. And is there anything else? No. So, okay, this is going to take a little bit of time, but we're going to go through it step by step. So first thing we're going to do is we're going to have init self, and we're going to define something. We're going to have some input size, and let's see the input size. Yeah, so the input size is basically going to be the size of the vocabulary. In this case, the German vocabulary, right? Because this is going to be the input to the encoder. Then we're going to have some embedding size, so that each word is mapped to some d-dimensional space, okay, basically. And then we're going to have hidden size. We're going to have number of layers of this LSTM. And then we're going to have dropout. And so we're first going to call super of encoder self init like this. And so I guess we can do self.hidden size is equal to hidden size, and self.num layers is just equal to num layers. And then we can sort of define all of the modules that we're going to use. So we're going to use dropout. So we're going to do self.dropout is nn.dropout with some value of the parameter of how many nodes to drop. So we're just going to send that in as dropout. That's maybe a bad name. Maybe we should name it like, I don't know, like P or something. And then self.embedding is going to be nn.embedding of some input size, and it's going to be mapped to some embedding size. All right, and then we're going to have self.rnn is going to be nn.lstm, and the LSTM is going to take as input. So we're going to run the embedding on the input, and then we're going to run the RNN on those embeddings. So the input of the LSTMs is the embedding size. And then the output, let's see. So the output from the LSTM is just going to be the hidden size. And we're going to have num layers, and then we're going to have dropout equals dropout, which, well, dropout equals P. So this is a what is it called? Key argument. Yeah, key argument. So then we're going to do define forward self comma x. So we're going to send as input, I guess, a long vector of all of the indexes of the word that is in the vocabulary. Well, that was a poor explanation. So basically, we're going to have a sentence. First of all, it's going to be tokenized, and it's going to be mapped to some index corresponding to where it is in the vocabulary. And then that vector is going to be sent into the LSTM. So this is a vector of indices. So what we're going to do first, so basically the shape of x is sequence length comma n, right? Where n is the batch size. And then we're going to do the embedding to be self.dropout of self.embedding of x. And so when we have the embedding, we're just going to call the RNN on this embedding like this. And so we're going to have some outputs, and we're going to have some hidden and cell output. And the only thing that we care about is the hidden and the cell. right? If you remember that figure I showed in the beginning, all we care about is the context vector, and the context vector is the hidden and the cell. So the output from this is irrelevant, and so we're gonna just return hidden comma cell. And let me just also explain the shapes of this, so nothing is missing in this tutorial. So we're gonna say like embed, the shape of the embedding is gonna be sequence length, right, comma n, which is the shape of x, but then each of those, so each word is also going to be mapped to some embedding size. Okay, so we basically added another dimension to our tensor, so that, I don't know, we can define the embedding size, but let's say it's 300. So for each word, there's now a mapping to some 300 dimensional space. Okay, so now that we have the, let's see, we have the encoder and we know that we got the hidden and the cell. We're gonna start with the decoder, and let's do the same thing, define init, and we're also gonna take self, input size, the embedding size, hidden size, and then we're also gonna have some output size, which, so, you know, the input size here is gonna be the size of the English vocabulary, right? But if you think about it, the output size is going to be the same as the input size. Okay, so we're going to output some vector which corresponds to values for each word which is in our vocabulary. So basically, if we have I don't know, like if we have 10,000 in our vocabulary, in our English vocabulary, so we're going to have like a output which is 10,000 dimensional, where each node represents sort of the probability that it's that word in the vocabulary. Okay, so then the input size is going to be the same as the output size. But so we could have just written this as like output size or input size, but just to be very clear. And then we're going to have the number of layers, and we're going to have some dropout. And as usual, we're going to call the super and self.init. And so let's see, what did we do? We did self.hidden size to be hidden size, and then self.numLayers to be numLayers, and self.dropout, like this, is going to be nn.dropout. And yeah, so we did and dropout of p, and yeah, so we got to do the embedding, which is going to be nn.embedding of some input size and map to some embedding size. And yeah, so let me also, well, actually, let's do that in the forward. Let's just define all of the methods that we're going to use, or the modules, and then self.rnn is going to be nn.lstm, and the input to the LSTM is going to be the embedding size mapped to some hidden size, number of layers, and then dropout equals p. And yeah, also one thing that's important is that the hidden size of the encoder and the decoder are the same. So just one thing to keep in mind. And then we're going to have also a fully connected, which is going to be an linear of hidden size to some output size. And again, the output size is just going to be the length of our, in this case, our English vocabulary. We're all going to define all of those later, but so we're going to do the forward self.x, but it's also now going to take in the hidden and the cell. Okay, so the context vector we talked about. And then one thing I need to say here is that the shape of x is going to be n, like this. But we want it to be, but we want 1, n, because what the decoder is going to do, it's going to predict one word at a time. Okay, so given the previous hidden and the cell state and sort of the previous word, it's going to, or I guess, yeah, the previous predicted value, the previous predicted word. So let me bring out this figure again. So sort of it predicts good, and then it's going to take in good right here, and then sort of also the previous hidden cell, and then it's going to output a one word. So sort of this is going to work word by word. And so this one here represents that it's just a single word. We have n batches of a single word at the same time. And this is in contrast to, the encoder, which had sequence length of words at a time, because in the encoder, we can just send in the entire German sentence. But when we actually do the prediction, we're doing it one word at a time. So this is easy in Pytorch. We're just going to do x.unsqueeze of 0. So we just added one dimension. And now we can send it to the embedding. So we can do self.dropout of self.embedding of x. And this is going to just be called our embedding. And then, so I can do these shapes again. So embedding shape is just going to be 1, n, embedding size. Yeah. Then we're ready to send it in through the LSTM. So we're going to do self.rnn, and we're going to do embedding. It's going to take the embedding as input. And then it's also going to take the hidden and the cell, right? The hidden and the cell we sent in here. So this is going to be, we're going to get the outputs, but then we're also going to get the hidden and the cell. And we got to keep track of all, because all of these are important now, because we're going to use the hidden and the cell for the next prediction, sort of the next word we predict. And the outputs, of course, is just the output for this, what we think this next word should be. So let me again, shape of outputs is going to be 1, n, hidden size. And is there anything else I want to say here? No, we're going to do one more. So we're going to do self.fullyConnected of outputs. And this is going to be called our predictions. And so basically, the shape of predictions is going to be 1, n, the length of vocabulary, so our English vocabulary. And this is then going to be sent to, our loss function later on. But what we want to have of the shapes is that we want to remove this one now. So, let's just do predictions dot squeeze of 0, and then call this our prediction. And then we can just return. Let's see, why did we want to remove this dimension? I think it was because when we send it to the, when we send it to the loss function later on. Let's see, let's keep that in mind. Let's see if I remember why we wanted to remove that one. But essentially, all of these things are like, we need to make sure that your shapes are the way that Pytorch wants it. And sort of, it's kind of a guess and try. Like you try something and the shapes didn't work. Okay, what does it want? And then you just adapt it until it works. So that's, yeah, so there's nothing like major thinking behind these shapes right here. I'm just trying to explain the top pattern behind why I'm doing the shapes and what the shapes are currently at, so you sort of follow every step. Yeah, I just wanted to add some words on this, why we squeeze the first dimension. So it has nothing to do with loss function directly. So essentially, we're predicting one word at a time, but we of course want to predict all of the words in the target sentence. So what we're gonna do later on, when you're going to see in the sequence model, we're going to sort of add the output from the decoder one step at a time, and then having this shape make sense. Yeah, that's the best explanation I can have. It's going to make sense later on. Anyways, moving on. Anyways, then we're going to return the predictions, but we're also going to return the hidden and the cell. And let's see. So now that we have our encoder and we have our decoder, now we're ready to combine those two. So we're ready to create our model essentially, and our model is going to be this sequence to sequence. So we're going to define init we're going to do self, and we're going to send in the encoder and the decoder. Then we're going to do super of sequence to sequence of self dot init, and we're going to do self dot encoder is just going to be encoder. Self dot decoder is going to be, you guessed it, decoder. And then we're just going to do the forward one. So let's see, what are we going to send in here? So we're going to send in our the source sentence, like the German sentence, and then we're also going to send in the correct target sentence. And I'm going to explain that a little bit more. So we're just going to send in the source, and we're going to send in the target, so the correct translation. And then I'm going to use one more thing. So I'm going to use teacher force ratio. We're going to set this to 0.5. So let me explain this, what this is used for. So, you know, as I said, let's bring out this figure again. So as I said, it's going to run at the beginning. It's going to have a start token, and it's going to predict one word. And then it's going to, you know, take this word, and it's going to be the input to the next, I guess, cell. Okay, so that it can predict the next word. Well, sometimes you want it to use, you know, this prediction is not always correct, and you don't want it to send in the incorrect one for the next cell, because that would just that would ruin a lot of sentences. So for training phase. So what you want is, you probably want to do some prediction right here that can later be used for creating the you know, calculating the loss and so on. But then for the next cell, you actually send in the target one, like the real one, or what it should translate to. And that's why we send in the target. And then for the, let's see, the teacher force ratio is that sometimes we're going to use the correct one right here, and sometimes we're going to use a fake one. I mean, not a fake one. So the predicted one, the predicted one from the previous cell. Okay, so sometimes we're going to take the prediction, and sometimes 50% of the cases we're going to choose the target translated word, what it should have been. So sort of the reason why we do this is we don't want the teacher force ratio to be 1, i.e. to be the correct target words all the time, because then at test time, the words that it predicts might be completely different than what it sees at training time. All right, I talked too long about that one. So anyways, we're going to do batch size, and this is going to be source.shape of 1. And yeah, that's just shape of it. So we're going to send in, let's see, source. I think, yeah, so source is going to be, don't quote me on this, but I think it's going to be target length, comma, the batch size, if I remember correctly, or comma n. So yeah, anyways, the batch size is going to be the second dimension of the source shape, and then target length is going to be target.shape of 0. And then let's do target vocabulary size is going to be the length of the English vocabulary. All right. And we created the, let's see, let me scroll up. Here we created the English vocabulary. So we can just do length of English.vocabulary. And then let us start with doing the output to be, well, actually, let's do, so remember, what we're going to do now is that we have the encoder and we have the decoder, and we're going to run it through the encoder to get our hidden and the cell, and that's going to be the input to the decoder. And so the first thing we're going to do is we got to build up those hidden and cell state. So we can do, you know, hidden comma cell to be self.encoder of source. Is that my cell phone right now? All right, I'll be right back. All right, so don't people know when I'm making videos? Anyways, so where were we? We have target vocabulary size, and then hidden and self from the self.encoder. All right, what's the next step? Well, the first thing we're gonna do is we're gonna have the start token. So we're gonna do x equals target of 0, so that this will be the so grab start token. And then what we're going to do is we're going to send in this to the decoder, right? And we're going to do this word by word. So let's do for t in range of 1 comma target length, and then so we're going to do output hidden comma cell. So we're going to call the decoder self.decoder of x, and we're going to use the hidden and the cell from the encoder. So we're going to also input hidden and the cell. And then, so the output from this is going to be the next hidden in the cell, which is going to be reused in the loop, right? So then we're going to do, actually, I forgot one thing. All right, so what we're going to do also is we're going to add here outputs to be torch.zeros of target length, batch size, and then target vocabulary size. And then we're going to also do .to device. So essentially, we're going to predict one word at a time, right? And for each word we predict, we're going to do it for an entire batch. And then every predicted is going to be, sort of that vector of the entire vocabulary size. So when we do one output right here, it's going to be batch size, comma, and then target vocabulary size. That's going to be the size of the output tensor. And then we're just going to sort of put that on this dimension right here. All right, so that was a poor explanation. It's going to make more sense. So we're going to do output of t, and then we're going to equal that to output. All right, and we're adding it along that dimension, the first dimension. Okay, and then we're going to get the best guess, which is going to be the output, and then the argmax of 1, right? Since it's outputting in the second dimension, right? So it will be the output will be, wait, I didn't mean to run that. So output will be n, comma, and then English vocabulary size. And so for each batch, if we take the argmax of this dimension, we'll get the index of the best guess that the decoder outputted. All right, so then what we're going to do, we're going to do x. So the next input to the decoder is going to be target t if random.random is less than teacher force ratio, else best guess. Okay, so the next input to the decoder will be the target word if this random.random, which will be between 0 and 1, is less than this teacher force ratio that we input to the model. So 50% of the times it's going to get the actual one, and the rest it's just going to get the guess from the decoder. Then at the end of this loop, we're just going to return outputs. Okay, is there anything else? I think that's it actually. So now we've come to the point where we have the model and we have done the encoder and decoder. Now we just gotta set up the training phase, right? So let's do. Now we're ready to do the training. Well, that was a lie. We need to define everything first. So we need to do training, hyperparameters. We gotta do model, or model hyperparameters, I guess. So we're gonna do like number of epochs. Let's do like 20. Learning rate, let's do 0.001. And then batch size, let's do 64. Gets pretty standard so far. And then we could do like load model equals false. And then we're gonna do device, torch.device CUDA if torch CUDA is available. Else we're gonna use the CPU. And yeah, so the input size to the encoder is just gonna be the length of the German vocabulary. And then the input size to the decoder will be just the length of the English vocabulary. The output size is gonna be the length of the English vocabulary as well. And then we can define the encoder, the embedding size. So let's say, I don't know, 300. And then the decoder embedding size, 300 as well. I think 300 might be actually a large dimension for the embedding size. So I've seen people use like 100 for the embedding size, but I think that's on the smaller end. So I guess somewhere around 100 to 300 is a good number. And then we're going to do the hidden size let's do 1024. And I think so for the paper review on the sequence to sequence, that they used a hidden size of 1000 or something like that. But I think that's small for today's standard, since that paper was from 2014. I don't know. It's, I guess, a medium size today. So then we're going to do the number of layers, and let's do just 2 layers. I think in the paper they did 4. Let's just do 2 so it doesn't take too long. And then let's do encoder dropout to be 0.5, decoder dropout to be 0.5. And one more thing, let's do something for the TensorBoard. So we're going to do writer. By the way, check out my video on TensorBoard if you're unsure about this. But we're just going to do summary writer runs loss plot. So all we're going to do is we're just going to essentially we're going to just do it to get a loss plot so that we can see sort of how the loss is decreasing. And also we're going to do step equals 0. All right, that was a lot to do. And then we got to also do the get iterator. From what I said in the beginning of the video, we also got to use the bucket iterator to split the data. So we're going to do train iterator, validation iterator, and then the test iterator is bucket iterator dot split. And we're going to send in the train data, validation data, and the test data. And one note on this, make sure that they match. So the train iterator is first, and then this will be the train data. Validation iterator is second, and then the validation data is second. Okay, so then we're going to do the batch size, which is just going to be equal to batch size. And I guess one thing that I didn't talk about that much in my Torchtext tutorials is that you can do sort within batch. We're going to use that. So this will be true. And let me write this line and I'll explain what it does. We're going to do sort key is lambda x, and then we're going to do length of x dot source. All right. So what this does is that we have all of these sentences, right? And they vary in length. What the bucket iterator is going to do when we have sort within batch true, and then the sort key right here, is that it's going to prioritize to have examples that are of similar length in a batch, right? And why we would want to do this is because we want to minimize the number of padding so that we can sort of save on compute. All right, and then we're going to do device equals device. And all right, and then I think we're just going to call. So we're going to do encoder.net to be the encoder. And we're going to send all of these arguments in. So we're going to send in input size of the encoder, encoder embedding size. We're also going to send in the hidden size. We're going to send in the number of layers. We're going to send encoder dropout. And then we're going to make it to CUDA if it's available. And let me just copy this because we're going to do, I guess, pretty much the same. Let's see, decoder net, and then we're going to call the decoder. And this should be decoder right here, and also decoder embedding size, hidden size. This should be the output size, and then number of layers, and then decoder dropout dot to device. All right, we're going to do the model. We're going to do sequence to sequence, and we're just going to send in the encoder and the decoder. And lastly, we're just going to make it to device. All right, we're almost there, I promise. We got some more things to do. So we're then going to do, this is going to be a long video, I think. Anyways, we're going to do pad index to be English.vocabulary.string to index of the pad in the pad string. And then we're going to do the criterion, and we're just going to use the cross entropy loss. And we're going to input one keyword argument here. We're going to use ignore index is equal to pad index, so that we don't, if we have padded it, because it's going to, so that all of the examples in the batch are of similar length, then we don't want to pay anything for that in our cost function. All right, and then we're going to use if load model. We're going to do load checkpoint, torch.load, and then my checkpoint.pth.tar, and then model optimizer. Right. And I think, so yeah, I think I forgot. Let's see. I got to load that as well. And So I'm going to do from utils. And this is a separate file that I created, and I just wrote some, I guess, nice functions to have. Like we're going to do translate sentence. We're going to calculate a Bleu score, and we're going to do save checkpoint and load checkpoint. So the to save the model and load the model, I've made an entire separate video on that if you want to check that out. And then for the Bleu score and the translate sentence, that's just two nice util functions that we're gonna use. I'm gonna probably talk about them and show the implementation in a separate video, just now to make this like over an hour, because I don't know how long this video is gonna be right now. So then if we're gonna use false, yeah, at the beginning, because we don't have a model. Then we're going to do for epoch in range of num epochs, and we're going to do print, we're going to do epoch out of number of epochs, like this. And then we're going to do checkpoint is state dict, and we're going to do model dot state dict, and then optimizer, and this is just standard code so that we can save the model. State dict, we got to have all the parameters, and then we're just going to call it to the save checkpoint of checkpoint. All right, then what we're going to do is we're going to do for batch. For batch index comma batch in enumerate train iterator. Then we're going to do input data is equal to batch dot source, and then we're going to just make it to CUDA, and then the target is going to be the batch dot target dot to device. And so one thing we got to do now is that we got to just send this to our model, right? The input data and the target. And then the output right here is going to be, so the output shape is going to be the target length, and it's going to be batch size, and then output dimension. Okay. So there's a problem here, is that in that cross entropy loss wants to have sort of a matrix. This would be a 3-dimensional tensor. But so for example, let's say that we would have the MNIST dataset. We would have n comma 10 to be the output, sort of n examples at the same time, and each example outputs 10 for each digit. And the output, so and then the targets would be just this shape, right? And we got to do similar here, in that, so you can sort of view that we have a batch, right? And for each batch, we sort of have 20 outputs from this model. Well, one thing we can do is that we can concatenate, or we can, I guess it's called concatenate. We can sort of put these dimensions together so that each batch has, I guess, like the target length amount of output that's going to be sent into cross entropy loss. Yeah, I don't know if I confused you right there, but anyways, all we're going to do is we're just going to do output, and we're going to do some reshaping. So we're going to do output, and we're going to do dot reshape. Then we're going to do -1, and then output shape of 2, right? So we're going to keep the output dimension, which would be the size of the vocabulary. And we're just going to sort of put everything else together. So we're just going to, I don't remember, what is the word? Not concatenate, but like, anyways, I lost the word. And then we're going to do target is target. Oh, one more thing, actually. We're going to do 1. Let's see. We're going to do 1 and then rest. So essentially, the first output right here is going to be the start token. But we don't want to send that to our model. So we're just going to remove that, and we're going to do the same for the target. And we're going to do reshape for this one as well, and so that this one is just a single dimension, so that this would take target length times the batch size, and that would be the shape of target. Then we can do optimizer.zeroGrad. Loss is going to be the criterion of output and target. Then we can do loss.backward. We can also do another thing, which is sort of to avoid that the gradients become too large, so that we avoid exploding gradient problems. We can do torch nn.utils.clip grad norm, and then model.parameters, and then we can do max norm equals 1. And this is just to sort of make sure that the gradients are in a healthy range, I guess. And then we do optimizer.step. And yeah, I promise we're almost done. We just have like 2 more lines. So we're going to do writer.add scalar, training loss, and then the global step is equal to step. And then we're just going to do step plus equals 1. All right. So now, believe it or not, we've created the entire thing. We've basically created Google Translate. All that we're going to do now is we're going to run this for 20 epochs, which is going to take a while, but that's the best part, you know, when you've created everything. Now it's just time to relax, sit back, drink some coffee, just have a good time. And so I'm going to press the button and whoa, okay, I thought I was going to have a good time. Tokenizer not defined. That's like in the beginning too. Let's see. Tokenizer right here. Tokenizer. All right. Tokenizer. If that was the only error, then I'm very happy right now. And it seems to work. All right. I'll see you guys in a bit, in about 1 hour. All right. Be right back. Okay. So we did get one more error, which is that this is not validation. This is going to be validation data, not valid data. All right. Let's rerun this. And believe it or not, we got one more error. So let's see. We got to do our optimizer as well. So we're going to do optimizer equals optin.atom model.parameters, and then the learning rate will just be learning rate. And hopefully that was the last one. Let's rerun this. All right, so it's training now, and it seems to work. But I got one more idea that I would like to do. So I took one sentence here from the let's see, right here, sentence. So I took this. It's quite a long sentence right here, and yeah, let's keep it on one line, or we could do like, yeah, we can keep it on one line. Anyways, this very long sentence here, I don't know, it was something like, I don't know German, but it's like a boat was pulled by a large team of horses or something like that. So this is in the training data, and I thought it would be interesting to just like see how this translated sentence would improve as the epochs go on. So I was thinking we could do model.evaluate, and then we can do this translate sentence that I used, that I created, and I'm going to show that one in probably the next video. But anyways, we can send it to translate sentence, and we can do model and then the sentence, and we got to send in the fields as well, and then the device, and then the maximum length of the prediction. So this will be just purely we're just going to send in this string, and we're just going to get what does the model predict that it's going to be. And we can do sort of like print translated example sentence, and we can do a new line, and then we can do translated sentence, and then we can do model train again. All right, so the model.eval is just gonna, I guess, turn off the dropout in this case. Yeah, I just thought that would be interesting. Let's now run this and let it train. All right, I gotta just show you what this sentence was actually saying. So this sentence right here that I took from the training data, it said, a boat with other men is pulled to the shore by a large team of horses. Okay, and I trained the model. So I'm gonna bring this over here. And yeah, I trained it on a couple of occasions. So I just printed it to, I just wrote it in a notepad++ file. So anyways, on the first epoch, it said, well, actually there's another epoch that I forgot to copy, and that was essentially like just random words. And I guess this is also random words, but it was more random words. So it didn't have this end of sentence token. But yeah, so I guess this is the second epoch technically. So then it was like a young player is a, and you'll see a lot of these a and the or is or those words, since they are very similar in the data. So it's not uncommon to just see like a, and that's all the model predicts. All right, and then let's see for the next epoch, a runner in a with a in the background. All right, it doesn't really make sense. Like it has nothing to do with boats or anything like that, but at least sort of doing something that makes, I guess, some sort of sense. A baseball player with a is the I guess that doesn't make any sense. A football player in a is being ready to a, okay? And then it comes a boat with his men is being pulled by a large building. I mean, it got some things right in this one. And then a boat with a full of a is being pulled by a large. So we can sort of see, the model is actually progressing. It's doing something that makes sense, right? A boat is being pulled by a large. End of sentence. And then a boat is being pulled by a large building. Building again. A boat with a is pulled by a large, being pulled by a large. Okay. A boat with two men being pulled by a large. Okay. A boat with no passengers is pulled by a large Ford by a large. Okay. I mean, what is interesting here is that it's being pulled by something. And then I guess by something again. A boat with two men being pulled by a large cable. I'm not sure how it arrived at that one, but anyways, you can sort of see. Let's see this the last one here. A boat with several men pulled by a large cable. All right, so it's sort of getting there, right? And I should have copied all of them, but I trained it for like 50 epochs more, and I didn't copy it, so we don't see it. But at least we can see how it does now. So when I rerun it now with these saved parameters, it's a boat carrying several men is pulled by shore by a large team of horses. And all right, you might be saying like, well, this data it's in the training data. It's of course going to learn those sentences. All right, it doesn't prove anything. Well, hopefully I'm going to prove you wrong. So we're going to do something like, we're going to use Google Translate. We're going to write an English sentence and we're going to translate it in German and see if we get the English sentence back. One thing to keep in mind is like the sentence has to be like a description of something, because there's like, I don't know, I tried first like writing like I really love peanuts and it didn't get it at all, because there's like no sentences that's written in that sort of, that I guess what is it called, in that form, like something that I like. It's more like a description, like that person walked and then yada yada yada. Two people walk in to the store to buy very cold ice cream. Sort of something like that. And then we can copy this. We can go back right here and we can do our sentence is going to be, we're going to copy that in and we can do, I have never done this. Let's see if this makes sense. So either you're right and this makes no sense, or we just created Google Translate. Two people going to a cross, getting ready to, end of sentence. All right, I'm going to defend myself right here. It's two people, and that was exactly what we wrote. And they're going somewhere, and they're not getting ready, but at least like it's getting some things right. We have to just train this for a longer time, and it would make perfect sense, probably. So one thing you could also do, as they did in the paper we read, is that you can calculate this Bleu score. And I'm going to copy that in. So we can probably do that at the end of training like this. And I'm going to do that. And I'm going to see, so we can do like this. And we're going to see what kind of Bleu score we get on the test data that it hasn't seen before, right? And yeah, I'm going to run this. It's going to take a while and I'll get back when it's done. So there was something wrong with the kernel and I had to restart it. But running it again, we get a Bleu score of about 21, which is, it's not that bad. It's all right. It's not that good either, but it's not terrible. So, we need to, we're not creating Google Translate yet. right? We have some work to do, which is awesome because then we get some more stuff to learn. So basically, I guess in the next video, I'm gonna review sequence with attention, which is an idea that you like, when you see it, you're like, oh, of course. But then again, every idea is, I guess, easy or simple in retrospect. So in the next video, we're going to do sequence with attention, probably review the paper, and then we're going to do implementation of that, and we'll see how much does that improve the Bleu score. And yeah, so this will be the start of a nice series, I guess. So hopefully you enjoyed the video. If you have any questions, then leave them in the comment section below. I think I said thank you for watching, but yeah, thank you for watching. Hope to see you in the next video.